Jai Hind everyone. My name is Ritesh. I am from AKGEC Engineering College, and I am taking subject the fundamental of electrical engineering. The code of this subject is BEE 101. Now the topic which I am going to take is today is the DC motor. Okay. So in the DC motor, the topic in DC motor, the topic which I will cover in this is working principle, the significance of the back EMF, torque equation, and if time permit, we will discuss about some the types of the DC motors. So in the previous lecture, as we have seen that the operation of the DC generator. In the DC generator, we have seen the how the construction and how the EMF is developed in the generator. Okay. Now we know that in DC generator, the energy is transferred or convert from mechanical to electrical energy, and in case of DC motor, we know that the energy is transferred from electrical to mechanical. That means when we give supply to the motor, the armature is rotated. That means it converts from electrical to mechanical. So first let us discuss about the working principle. So in working principle, as we all know that the DC motor, which is a device, as we know that, which convert the DC current into the mechanical work, because we provide, since it is a DC motor, we provide the DC supply, that is a DC, and it convert into the mechanical. And when we provide the current in the armature of the your motor, that means when the current carrying conductor which plays in the magnetic field, it will experience the force. We all know that. That is called the principle called the Lorentz force. When the current carrying conductor is placed in the magnetic field, it will experience a force, and that force is called the Lorentz force. And the direction of force can be determined by using the Fleming left hand rule. So we can know that we can determine the direction, in which direction your motor, your armature will rotate with the help of Fleming left hand rule and the Fleming left hand rule. In case of, we know that in case of generator we use the Fleming right hand rule, but here in case of motor we use the Fleming left hand rule. Now in the Fleming left hand rule, you can say that that is when we stretch our fingers, perpendicularly, we have a thumb, the index finger, and the middle finger. The index finger will indicate the direction of field, and the middle finger will indicate the direction of current in the armature or in the coil actually, and then this thumb will indicate the direction of motion of your armature or the force actually, where the force will act, your armature will rotate in that direction. So if the thumb and the middle finger and index of the left end are displaced by from each other by 90 degree like that, and the middle finger represents the direction of current and the index finger in the direction of magnetic field, the thumb shows the basically your thumb shows the direction of force acting on the conductor. So this is how you can do. Okay, this is simply a method to find the direction of force on the conductor, so that it will rotate in that direction. So this is a simple method. Now you can say that, suppose that we have the conductor. Suppose that a conductor is there. Let us understand this thing in more detail actually. So conductor in a fixed, suppose the field is this is your north, this is your south. So this is the direction of field, and if the current carrying conductor is lying on the field, suppose that the conductor is such that the current is going inside this plane. Sorry, the dot is there. We know that the concept dot and cross. The dot means that the current is coming outside. So it means that, so here the current is coming the outside the paper. That means you can see that if the current is this, field is this, now you can see that this force or this thumb will tell me the direction of force. This is how it is possible. Basically what happens, the field is coming from north to south, and when the current carrying conductor, since it has its own current, so using the right hand thumb rule, we know that the direction of fluxes is outside this, like this. These are the lines of forces as far as the flux of the armature, like this. It means that when we calculate the interaction of these two fluxes is this, because one is the field of the your poles field, and one is the flux or the field of the own conductor, because this conductor have the current actually. So it means that there is the strong field in this part of the conductor, and there is very less field in this part of the conductor. So always the force will act from strong to less. So this side where there is a strong force, it will like a rubber is stretched. When the rubber is stretched, so it will put the conductor in this direction, the force. So force will act in this direction. That we can determine using the left hand rule of the thumb. So that means if the conductor having current outward like this, again we can see this is the current direction, this is the your field. So this thumb will tell you the direction of force in this direction. So similarly, you can find the direction of current when the current is going inside this paper or in this board actually. So in that case, there will be a cross. When the cross is there, you can say that the current and the field is going, suppose that this is north pole, this is the N, and this is the S, this is the, you can see these are the lines of forces or flux for this, and since it is the cross is this, it means that the current is going inside this actually. So when the current is going, so flux will in these directions. So the direction of flux will be changes. It will be like this. Like this. So we can say that this is now if I can see that this is your current coil, and here you can say that the magnetic field will be strong in that direction, and in this direction the field will be very less, so that it will put the force to move the conductor in this direction. So by using this your left hand rule, if the current is going inside, the field is from north to south, it will be going these directions. So we can determine by simply using the left hand rule. So whatever is the direction of current in the coil, because it will depend upon on which pole it is lying, it will experience a force, and as a whole your motor will start rotating. So this is the basic principle behind the how the DC motor work or it rotate actually. Now you can see these are the certain figures which we can see. Suppose this is the north and south. So this is the north pole and south pole. So this is the poles, and this is the dot. Sorry, cross. That means current is going inside. So it means that it will force in this direction. Similarly, when there is a dot, so current will move, or sorry, force will move in these directions. So similarly, if we change the polarity, south, north, accordingly the current direction of current or force will be changes. So this is how we can say that the direction of rotation of the motion can be decided with the help of Fleming left hand rule. Okay, the concept of Fleming left hand rule. Now a very important topic with this back EMF is this. Now look at this circuit actually. Look at this circuit. In this circuit we can say that when we apply the voltage, what happens when the current carrying conductor rotate in the magnetic field, it will experience the force, and when the motor rotate, it means that it will link the flux. There will be the voltage generate, or some voltage will be there in the your armature. Now this voltage is called, which is developed in the armature, we call the back EMF. Now what is this back EMF? Let us understand the concept of back EMF. So when the armature of the DC motor rotate, the winding, as I told you that the winding or the conductor on the armature also rotates in the field, and according to Faraday's law of the magnetic induction, the EMF induced in the conductor, and whose direction can be decided by the Fleming's right hand rule. If we have the Fleming's right hand rule, we can decide the direction of field. Now that induced EMF will oppose the voltage, applied voltage, because of the Lenz's law, that is, which created. So that developed, this back EMF is developed by this applied voltage, that means it will oppose it. So it means that, and one function is this back EMF will be developed in the armature. This armature having some certain, because this armature is nothing but a winding, so it has some resistance also. So suppose RA is the resistance, we applied voltage. Now you can easily calculate the current in this particular circuit. And this is our armature. This is the armature of the your DC motor. So net current, that is the armature current, not net current. It is the armature current which you can calculate from here will be given by the net voltage upon the resistance, and the net voltage is nothing but the, this is the, if we apply the KVL, this is the net voltage, that is V minus VB. Now here the EB is nothing but it is a voltage which is developed in the armature, and since we know that the voltage when the rotor is armature is rotated, there will be induced EMF, as we have already gone through that. So this voltage, this value will be equal to phi Zn upon 60 into P upon A. This is the voltage generated in the armature, and we are calling it back EMF. Why we are calling it back EMF? Because its direction is opposite to that of the applied voltage, concept of Lenz's law. And this back EMF will try to oppose the applied voltage, but it has the driving current IA against this is. So this back EMF is responsible for this armature current. Since armature current is equal to how much? This IA is equal to your V minus VB upon RA. So RA is constant here, and applied voltage is also constant. So this means the IA is very much responsible for, depend on the value of EB, that is called the back EMF. And back EMF, if you can see that here, is proportional to, because we know that poles are constant, armature means the parallel paths are constant, conductors are constant, and the flux is almost constant. In that case, it is very much proportional to the speed, that we know that. So back EMF is proportional to the speed of the rotation of the armature. So this is very important part as far as the DC motor, because this concept is always only in this DC motor, not in the any AC motors. So this back EMF, we can just decide the constant of back EMF. So this is how we can try to attain the armature current. So armature current here, it will be decided by the back EMF, because whenever the back EMF will be whenever the back EMF will be low, that means the current will be high, and when the back EMF increases, the current accordingly, back EMF increases means speed is increases. So that will be understand the concept of or the significance of back EMF. So our topic is significance of back EMF here. Now, so all these things we have done, that is EB is this, we have covered this part also, that is back EMF is nothing but phi Zn into P upon a volt, where RA is the armature resistance, it's very small value, and expression for the induced EMF is given by this. This is the induced EMF, and we call it the back EMF actually. And it also depends upon the speed. So when the speed is high, always the back EMF having the high value, and hence the current will be small. And if the speed is less, the back EMF will be less, and accordingly the current will be high. That means more current will flow to develop torque, because torque is, you can see that torque means the armature torque is proportional to flux and IA. We will discuss that IA. If the flux is constant, the torque is proportional to current, armature current. So that means the torque is also the current is also responsible for the torque. Let us see how. Okay. So what we are studying here, the significance of this back EMF. Now we understand what is the back EMF actually. Now what is the basic significance of this back EMF? Let us understand this. So main first is the back EMF which opposes the supply voltage as to force current, because back EMF is always opposes supply voltage, and that's why it forces the current through the armature against the back EMF and to keep the armature rotated. So it always keep armature rotating, and the electric work done, which is you said that in overcoming and causing the current to flow against the back EMF is converted into the mechanical energy. But whatever mechanical energy is developed in the armature, that is depend upon the mechanical power in the armature, is given by this back EMF. And the mechanical power is nothing but it is EB into IA, because EB is the voltage developed in the armature and IA is the armature current. So power, you can say it's EB into IA is the power developed in the in the armature. Another point is a very important point, that is called the back EMF make the motor as a self-regulating motor. This is a very important characteristics of the DC motor, because of this back EMF, this motor is a self-regulating. How you can say that? The meaning of self-regulation. We know that this is the current. We just write this expression, IA is equal to V minus EB into IA. It is the current which is given, which is in the armature current actually, and this current is depend on the value of EB, that is back EMF, because V and RA are almost constant, because we cannot change the resistance of the winding, and the supply voltage is also constant. So that means it depend upon the back EMF, which depend on the speed. So IA is depend upon the back EMF, and the back EMF is proportional or the depend on the your speed of the motor. Now how this motor is significance means the self-regulating, it means that let us discuss the three cases. Okay, let us discuss three cases. One is when the motor is running at no load. Suppose the motor is there and this motor is running at no load, there is no load on the motor, that it means that the torque is, we know that the torque is proportional to current. So that is the torque which is required by the motor to overcome the losses, which is nothing but the windage losses or some kind of friction losses, and therefore a very small current is required or drawn by the motor armature, and back EMF is almost equal to supply voltage. So in this case, it is running at the rated or your no load, the current is very low, because the back EMF is almost or nearly equal to the voltage or the supply voltage. Okay, because it is running at that. So torque is proportional to IA, and since back EMF is proportional to speed, so whatever at speed which is rotating, the voltage is generated actually. That is called the back EMF. And according to the equation, that is IA, the V minus EB upon RA is this. So there is a very small current, because this value is nearly equal to the V. Now the next case is if the motor is suddenly loaded. Suppose if you put the load on the motor, then what will happen? When we put the load, there is a load torque, there will be some load torque, and this load torque becomes greater than the armature torque, because armature is providing some torque, and when suddenly the load torque increases, it means that load torque is greater than armature torque. It means that when it is loaded, your motor speed will decrease or slow down. The motor will be slow down. Okay, because the load torque is greater than this armature torque, the armature torque and motor start to slow down. When the motor speed is decreased, when the motor speed is decreases, we know that when the speed is decreases, the back EMF is again decreases, and with the decrease of this back EMF, what will happen? This numerator part will increase. This numerator part will increase. It means it will increase the current. So if armature current will increase accordingly, it means that the torque which is proportional to armature current will also increases. Since armature current is increases, torque will also increases. It means that the armature torque increases and at some point it becomes equal to the load torque, because the current or the torque, that torque we call the armature torque, will try to attend that load actually. So it will become equal to the load torque at some point, at some speed actually. So at that moment the motor stops slowing down and keep running at this new speed when it achieves that torque. Okay, because almost we know that this EB is decreased, current is increases, and if the current is increases, torque will increases, and accordingly it will attain that speed. So it will attain at that speed again. So this is how it will regulate actually, because it is suddenly loaded. So it will regulate accordingly. Another case where if the load on the motor is suddenly reduced. Suppose that if the motor is rotating at particular load, high load, and if the load is reduced. So what does it mean? It means that when it reduces, it will accelerate actually, because at that moment the torque is high and suddenly the load is reduced and the motor is accelerated. So that means its speed will, you can say, its speed is also increases and back EMF is also increased at that speed. And if the back EMF is increases, in that case the this portion will again decreases. That means the current will reduce. So you can say that again for this case the current equation will be equal to V minus EB upon RA. And if this we know that the speed is high because the load torque is reduced, the load is reduced actually, that means it means that speed is accelerated. So this whole numerator will be decreased. It means current decrease, and if the current decreases, we know that the torque again decreases accordingly because it is proportional to the current. So again, when the motor is suddenly reduced, the load torque is reduced, again the torque will be the armature torque, again it will be reduced because current is reduced, and it will attain the required load torque. So at some point it become equal to the load torque, and that point motor will stop accelerating and it will start rotating uniformly at this particular new speed. So it means that this motor is self-regulating. Automatically it will regulating by just reducing the current or armature current or increasing the armature current, so that the torque is reducing and increasing. And this shows the importance of the vacuum in the DC motor. That's why we call that this is a very important concept to understand, as we call it the significance of the back EMF. So these are the three cases that we discuss here as the significance of your back EMF. So after this, when the torque, we are talking about the torque, actually we have the torque. Let us discuss about the torque. What is the torque equation of the DC motor? So torque equation of the DC motor. So in general, if we discuss that, the torque is nothing but some force and some radius of the armature. Suppose that the radius of the armature is R, is some actual distance actually, and the work done in this by this force is given by force into distance, and the distance is nothing but the circumference actually. So that is 2 pi r. Okay, so force into distance is the work done. Now the net power developed is equal to given by work done per time. So net power is given by force into number of revolutions. Okay, so that force into circumference per time is given by force is given by this F into multiply by that distance 2 pi r divided by the time. Time means the time taken by the conductors in one revolution actually. In one revolution, suppose you can say that if in RPM, that is in 60 revolution per minute. So RPM is revolution per minute. So 6 revolution per minute, 60 seconds n revolution. So in 1 second, that is nothing but n, sorry, it's different. It is uh, it is in 60 by n. So in 1 second, in 60 second, we have n revolution. So in 1 second, this is n by 60. So in n revolution, इसको just we reverse it in 60 seconds. So in one revolution, we are talking in terms of one revolution. So in one revolution, it is 60 by n. So we can put 60 by n so that it becomes like this. So your total torque will be equal to force into, and this 2 pi n by 60 you can replace by omega. Okay. So what else is F into R into 2 pi n by 60 is this, and this 2 pi n by 60 is replaced by omega. So this is your F into R into omega, and this F into R is called torque into omega. So this is our power, net power developed. So this is the net power developed in the armature actually. Okay, and we know what is the net power actually. Okay, let us discuss then. So the armature torque, if we talk about the armature torque TA, so the net power, we just conclude that this is the net power. Power is equal to torque into some angular speed, that is omega, 2 pi n by 60. And the mechanical power developed in the armature is converted to the electrical power, because this power in your armature, some power is developed, and that power is nothing but it is the equal to the electric power is equal to EB into IA. That is the power in the armature. When we equate these two, power, this is the power developed in the armature, and this is the electrical power. So if we equate both this power, we will get the torque expression, and the torque expression will be given by this torque expression. You can from here is equal to, and you also replace this back EMF by its expression, you will get some torque equation like this. So you can say that torque will be equal to 2 pi's torque will be equal to we can write that. So this torque, armature torque rather, is equal to, if you come to it, phi zn upon 60n. So you can cancel out from n to n. Okay, and you can also cancel out this 60. So what else remains is your torque, armature torque will be equal to P into Z upon 2 pi A into phi into IA Newton meter. So this part is the constant term. So hence the torque is proportional to flux into IA in proportional to this. It means the armature torque is always depend upon these two factors, flux and current, armature current. And if the flux is constant, suppose for the shunt motor, we know that in shunt motor the flux field having the constant value. So ultimately the torque can be say that is proportional to current, as we use this in the previous while we are discussing about the back EMF. So it means that the armature torque and the armature torque expression, this is the torque expression, okay, and this is how the torque is related. Torque is depend upon the armature current, okay, it depend upon the flux and current actually. So this will this is the torque equation of the your DC motor, and certainly we have some types of this DC motors. The types of DC motors, if we talk about, we have the separately excited DC motor, okay, we have the self-excited DC motor. So let us understand the concept of self-excited, sorry, separated. In the separately excited means that this is our motor, okay, this is the armature, and when we excite this motor, this is our supply voltage, this is not the load actually. When supply, it is given to this, and your field winding is excited separately by some DC supply. So field, when you supply the field winding, this is what our armature is this. Now from this you can see that your armature is given some voltage, so V, that voltage V will be equal to back EMF plus the drop in this resistance, because since the current is flowing as this IA, the drop will be equal to IA into RA. And if we consider the brush drop, because these are the brushes, and if some brush drop is this, we take the as a V brush. This is the V brush, and sometimes we neglect it actually. Okay, and if it is given that, we can consider here. So this is the equation of the armature side, and the field is also is given. So as we know that in the separately excited, the field coils or the field windings are energized by separate DC source, and this is our armature, which is supplied by the source. In self-excited DC motor, the field winding is not separately, but it is self-supplied by the, it is excited by the armature itself actually, okay, or this voltage, this DC voltage, okay. So in this type motor, current in the winding is supplied by the machine or motor itself. So that's why we call it the self-excited motor. Okay, and further it is divided into a shunt wound and series wound. How the series field and the shunt field is placed in the circuit. So we can categorize them actually. In case of a shunt wound motor, in case of this is the example of shunt wound motor, we know that it is the shunt wound when the current is applied. Suppose it is a load current actually. This is the I, or the total current, or the line current rather. The line current is equal to the current going in the armature and current in the shunt field winding. So this I is equal to IA plus ISH, or IR is equal to IA plus ISH. Then this voltage V is equal to ISH into RSH, because it is parallel. So this V is equal to ISH into RSH, simple the concept hai. And again this V is equal to this. These are the equations as far as the shunt motor or the shunt wound motor is there. And in this case, the field winding is connected in parallel with the armature actually. This is the main characteristic of this. Okay. In case of series winding, we know that the series field winding is there, and which is connected in series with the your armature. So when there is a series, so the same current, armature current is same as the line current actually. So IL is equal to your the same current flow in the series field winding, and same current will flow in the IA. So this is the equation of the your voltage equation as far as the series field winding is this. So it means that the series winding having a very low resistance, so this winding having very low turn actually. In case of shunt, the turns are high, okay, because they are connected in parallel actually. Okay, so these are the two types of this self-excited and in shunt wound motor and series wound in DC motor. Another in the self-excited motor is that shunt wound and your series wound or series compound, shunt compound motor and series compound motor. Okay, so that we will discuss in our next lecture. So thank you so much.